So here we are. It is Thursday, November 12th, 2020. We're doing randomness in simulations. When it comes to randomness, right, probability allows us to predict what would otherwise be random and unpredictable. Right. One of the drawbacks is that probabilities are rarely correct in the short term. Right? And when things don't seem to fit, we tend to try and explain them without probability in mind. We try to come up with a reason as to why it didn't match what we thought should happen. Right. For example, suppose you flipped a coin 6 times. Which of the two outcomes below seem more probable? And in this H equals heads, T equals tails, we have these two possibilities here, right? Which one, the one on the left, or the one in the right, do you think is more likely? We have heads, tails, heads, tails, tails, heads. And we have heads, 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 tails, tails, tails. Based on what we know so far, which one of these outcomes would be more likely when flipping a coin 6 times? What do you guys think? Right. Jasmine says they both would have the same possibility, right? Interesting. Very good. Anyone else have an idea or a thought? Jocelyn agrees with Jasmine. All right. And you guys are correct. They are the same. Both of these outcomes are equally likely, even though maybe the one on the right seems a little less normal, right? It seems like it could be suspicious to have 3 heads and 3 tails. Technically, they have the same probability, the same likelihood of happening. Right, so the order in which the things happened isn't really a factor. All right. So probability only says what is likely to happen in the long run. Right? Over a short period, like 6 rolls of a dice or 6 flips of a coin, probability doesn't really come into play that much because it's a very short period of time and it's a very short number of repetitions, right? In the long run, about half the flips of a coin will be heads and about half will be tails. And we saw this, we talked about this in the previous class. The order in which the outcomes occur is not a factor and does not change the long run probability. Okay. So that's kind of the thing. Just because we have a run of things that happen in a row doesn't mean that the probability is incorrect, right? It means that we just had a run of things that happened. Right? That is why we have the law of large numbers. It tells us look at a large series of these events, a large number of simulations or outcomes to find a probability. All right, and we have the myth of the law of averages. The law of averages is not a thing. It's just something that's been created, so to say. So if you imagine flipping a coin 6 times and getting 6 tails in a row, right? If you believe in the law of averages, you might believe that the next toss should surely be a heads, as a heads is due to appear. Right? We've had, 6 tails. The next toss should surely be a heads. But the next flips is a tail. How could this be? Right? There's already been now 7 tails in a row. How could we flip that many times and not get a heads? Right? The probability says we should be 50-50 here, right? So the simple answer is the coin has no memory and doesn't care what you think. It's a coin. It has no idea that it just landed on heads or tails. It's just being flipped. All right. The idea with the law of averages is that it somehow knows what previously happened, and that is going to influence the next outcome. Right? Essentially, the myth is that future outcomes must make up for past imbalances, and that's just not the case, right? The coin doesn't know, right? When you roll a dice, it doesn't know what it last landed on. The probabilities are just based on the long run of a bunch of these outcomes happening and the numbers and what happened, right? It has no influence on the next outcome, right? In the long run, things will even out. This is the law of large numbers playing out, not the law of averages. Right? That is not a thing when it comes to probability. Right? So yeah, this lesson today doesn't have a ton of like math in it. It's just kind of like what is probability still, and kind of how it comes up. Any questions so far? So now we get into a simulation. We have a definition for what a simulation is. Right, the imitation of chance behavior based on a model that accurately reflects the situation is called a simulation. Makes sense. We've all done simulations. Yeah, we did one last class. Right, the 1 in 6 game we played, right, where we rolled the dice to simulate buying sodas and winning a prize. That should say prize, not price. Right, the simulation allowed us to quickly determine if the probability was reasonable without going out and buying sodas, right? We didn't actually have to play the game that was being modeled, right? We didn't have to go and buy sodas to determine if the outcome was reasonable, right? We just rolled dice. We can do that quickly and easily, and it models the situation quite well. All right. Are there any questions about what a simulation is? All right, and so then we have the 4 steps of performing a simulation. We want to try and use these same 4 steps every time we do a simulation or every time we talk about running a simulation or how to do a simulation. All right, step 1, state. Ask a question of interest about some chance process. Right, in this case, we are specifically talking about chance processes, right? We're talking, that's what this unit's about. Right? Probability has to do with chance. Plan. Describe how to use a chance device to imitate one repetition of the process. Tell what you will record at the end of each repetition. Do. Perform many repetitions of the simulation. And step 4, conclude. Use the results of your simulation to answer the question of interest. Right, so these are the 4 basic steps of performing a good simulation. Right. The most important part, essentially, as far as I'm concerned, is the plan. Right. Having a well thought out and well described plan before you start doing your simulation. Right. Don't just say we're going to roll dice or we're going to flip a coin. What is that representing? Which does heads or tails have a significance? Does the numbers 1 through 6 on the dice have a significance? Right, having to provide those details is all part of the plan. All right. So, can you raise your hand if you need a moment to write these things down? Okay. All right. Looks like we're ready. So let's look at these 4 steps in the 1 and 6 wins game, similar to the one that we did on Monday. All right. So step 1, state. What's the probability that 3 or more of 7 people who buy a soda win a prize if each bottle has a 1 in 6 chance of saying you're a winner? Right? That's the problem that we're trying to answer with our simulation. The plan: use a 6-sided die to determine the outcome for each person's bottle of soda. A 6 wins a prize, a 1 through 5, no prize. Roll the dice 7 times, once for each person. There were 7 people, we rolled it once for each one of those people. Record the number of people who win a prize. And that's what we did in our simulation on Monday. Right, the do part, have each student perform several repetitions. Again, that's what we did on Monday. We answered a slightly different question on Monday. We were just trying to find out, is the 1 in 6 that they're claiming reasonable? They're asking, what's the probability that 3 or more of the 7 people who buy a soda win a prize? So out of 125 total repetitions of the simulation, there were 15 times when 3 or more of the 7 people won a prize. So our estimate of the probability is 15 out of 125, or about 12%. It seems plausible that the company is telling the truth. Right? There's not an exorbitant amount of people winning a lot. Right? There's only 12% won where 3 or more people won out of 7. Right? So this is just an example of the state, plan, do, conclude, and the type of details that should be provided in each of those steps. Okay. So you may need a moment to write any of this down. Please raise your hand. Good. Okay. So then, let's see if I can make this work. We're going to look at another example from the textbook showing this process. Yeah, I'm gonna have the link in the class resources for this video as well. I'm gonna have to. I would end the meeting and start it again, but we'll just try to get to the end of this lesson. We don't have a lot left, and I gotta mess around with my setup again to try and get things to do what I want them to do. So I apologize. But yeah, things are just not cooperating as I would like. At all. So I apologize, guys. Super annoying. All right. Okay. So we're gonna try and push through to the end of this thing here. All right. So this is the last thing we have here. Hopefully something will work kind of on this. So we're looking at another situation here. Suppose that the probability of flipping a coin was not fair. Now the probability of a heads was 0.6 and tails was 0.4. So you have a 60% chance of a heads and a 40% chance of a tails. What would you have to do to simulate this properly? Right? We can't really flip a coin anymore in this situation because any coin that we have is a fair coin for the most part. So that means that we have to come up with another way of simulating this process. This is just not going to work as I want. Oy vey. All right. So what we can do, right, is use a random number generator rather than flipping a coin, right? And so in this case, we can assign heads. Maybe this is making this really hard. We're just going to show up. Nothing at all what I wanted. Losing my mind here, guys. I apologize. Okay, the mouse wants to work, but my little tablet thing doesn't want to work. All right. All right, I'm going to talk through this. I do apologize. This has been terrible, and I apologize profusely for the lack of things working. In this case, the best thing to do is assign heads to the numbers 1 through 6, right? And tails to the numbers 7, 8, 9, and 10. There's 6 numbers in a random number generator that apply to heads, 60% of them. 4 numbers in a random number generator that apply to tails, or 40%. So you have a random number generator that generates numbers between 1 and 10. And you run this thing and you record if it's from 1 to 1, 2, 3, 4, 5, 6, that goes down as a heads. 7, 8, 9, 10 goes in as a tails. And so you'd have to use this alternate method to run your simulation because flipping a coin doesn't work anymore because there is not an equal chance of the outcomes occurring. Okay, so what that means, why I'm going over this. No, I don't want that, guys. Come on. In our discussion board for today, we're going to look at that NASCAR example again. So if it didn't make sense, again, I'll have the link in the class resources for today. In that example, each of the cards had the same chance of being in any given box of cereal. That is, they were each equally likely to happen. There wasn't one card that had more chances of being found in a box. What if the cereal company decided to make it harder to get some drivers' cards than others? For instance, what if the chance that each card appears in a box of cereal is Jeff Gordon gets 10%, Dale Earnhardt gets 30%, Tony Stewart is 20%, Danica Patrick's 25%, Jimmy Johnson is 15%. So they each have a different percent chance of being in your box. How would you modify this simulation? All right, they're not equally likely, so I cannot use something that has an equally likely probability itself. So in the previous one, we could like roll a dice, so to say, because a dice has an equal chance of any of the sides happening. Once it's not equal, we have to come up with another plan. In this case, possibly using similar to what we did in the unfair coin, using a random number generator and assigning a certain proportion of the numbers to be for each of the cards or each of the drivers. Okay, so that's the hint / explanation for why I tried to do that last example. Okay.